What are slip lines and how do they show plasticity? Imagine looking at a tiny metal piece under a microscope and seeing thin straight lines running across its surface. These are called slip lines, and they tell us a lot about how materials change shape. When a material is bent or stretched beyond its elastic limit, it doesn't just spring back. Instead, it undergoes permanent deformation, which is called plasticity. Slip lines are like the footprints of this process, showing exactly where and how the material has shifted. Slip lines form because of something called dislocations, which are tiny defects inside the crystal structure of metals and other crystalline materials. Think of dislocations as small breaks or misalignments in the orderly arrangement of atoms. When stress is applied, these dislocations move along specific planes and directions within the crystal, called slip systems. As they glide, they cause the layers of atoms to slide past each other, creating shear strain. This movement is what allows the material to change shape permanently. Now, these dislocation movements don't happen randomly. They tend to follow certain paths, which appear as narrow, straight lines on the microscopic level. These are the slip lines. They are visible because the shear strain causes slight changes in the surface or microstructure, which can be seen under a microscope. The pattern and density of slip lines can tell engineers how much plastic deformation has occurred and how the material has responded to stress. Slip lines are important because they reveal where the material has localized strain. If too many slip lines appear in one area, it might indicate that the material is nearing failure or cracking. This is because concentrated slip can lead to the formation of cracks or other defects over time. By studying slip lines, engineers can predict how a material will behave under repeated or extreme loads, helping to prevent unexpected failures. The formation of slip lines depends on several factors. The composition of the material influences how easily dislocations can move. For example, alloying elements can either hinder or promote dislocation movement. The size of the grains in the material also matters. Smaller grains tend to produce more slip lines because dislocations have less space to move. Processing methods like cold working increase dislocation density, making slip lines more prominent. Temperature plays a role too. Higher temperatures allow dislocations to climb and cross-slip, changing how slip lines look and behave. Understanding slip lines helps us see the internal story of a material's deformation. It shows us where the material has yielded and how it distributes strain. This knowledge is vital in designing stronger, more durable products and structures. For example, in manufacturing steel components, observing slip lines can indicate whether the material has been overworked or if it is still safe to use. It also helps in developing processes like metal forming, where controlling slip is essential for shaping metals without causing cracks. In essence, slip lines are like the fingerprints of plasticity. They reveal the microscopic dance of atoms and defects that allow materials to bend, stretch, and sometimes break. By studying these tiny lines, we gain a clearer picture of how materials fail and how to improve their performance in everyday products and critical structures around us.